Hello, and welcome to Lecture 3 in Equilibrium Chemistry. Today we're going to look at Le Chatelier's principle. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis for the bulk of the diploma exam questions that you'll see. Hopefully you're referring back to this page from time to time to get a sense of how well your progress is coming. Equilibrium Chemistry presents some unique challenges to industry. Some chemical systems produce very valuable end products, but their equilibrium position greatly favors reactants. Desirable end products aren't produced in significant quantities to be economically viable. One such process, known as the Haber process, involves the industrial manufacture of ammonia from nitrogen gas and oxygen gas. And here's the reaction. It's got a very small Kc value, 6 times 10 to the minus 2 at 500 degrees. This reflects a reaction that greatly favors the reactants, producing a very small yield of ammonia. Industry has learned to manipulate this position to increase the yield. Le Chatelier's principle underlies this area of chemistry. It states that when a chemical system in equilibrium is disturbed, the system will shift to oppose that change until a new equilibrium is reached, typically defined by the same Kc. This principle was used to improve the yield of ammonia from the Haber process by manipulating both pressure and temperature. In this course, we'll focus on several factors known to cause chemical systems to shift. The first of these is concentration. The reaction below is an industrial process for the production of freon, which is a refrigerant, and the system will reach its characteristic equilibrium position defined by its Kc. So here's the reaction, and here's its Kc. And you'll notice that the liquid phase tetrachloromethane is not included in the Kc because it's got a constant concentration. Here's a graph of concentration against time for the reaction, and you'll see that at T0, that we start with some positive concentration of the gas phase reactant of the hydrogen fluoride. And its concentration comes down, and at the same time, the concentrations of the products start at 0 because we don't start with any products, and they go up. The hydrogen chloride goes up twice as fast as the freon because the stoichiometry is 1 freon particle is produced for every 2 hydrogen chloride particles. The vertical line represents dynamic equilibrium, but then a disturbance is presented to the system. What they do is they add gas phase hydrogen fluoride, which is the only gas phase reactant in the system. The system, of course, shifts to reduce that stress, so it shifts to the right. And I'm going to use the expression shift to the right, shift to the left in this lecture. I'm also going to say favors reactants, favor products. When I say shift to the right, I mean that products are favored and that the concentration of products will increase in response to the stress. And you see that here. The concentration of the HCl and the concentration of the freon both increase in response to the addition of the HF. When I say shift to the left, I mean that reactants are favored and the concentration of reactants are going to increase in response to the stress that's been introduced. So if we add additional hydrogen fluoride, the system shifts to the right to favor products and to reduce the concentration of the hydrogen fluoride. So the concentration of the products are increased, as we saw in the graph, and the concentration of the gas phase reactant is decreased. And again, note, if you go back to the Kc, note that the CCl4 in liquid phase is not included because it has a constant concentration. More importantly, the addition or removal of some of the CCl4 in liquid phase does not affect the equilibrium position of the system because we're not impacting on its concentration. This is very different, though, than when you add the hydrogen fluoride, which is in gas phase. By either adding it or subtracting it, you're most definitely influencing its concentration, and therefore you're going to cause the equilibrium to shift to reestablish the same Kc. And manipulating concentrations like this by adding reactants and removing products is probably the most common industrial method to shift an equilibrium position to favor products. For example, following is the last step in the manufacture of nitric acid. The process is pulled to the right by removal of the nitrogen monoxide by reacting with oxygen gas. So here's our reaction, and you'll see there's two end products. One is our aqueous phase nitric acid, which is our desired end product, and the other is a gas phase nitrogen monoxide. And we pull this system to the right. In other words, we increase the concentration of products of the system by removing the nitrogen monoxide by reacting with oxygen gas. The oxygen hemoglobin system is an interesting biologically important dynamic equilibrium, and it also demonstrates Le Chatelier's principle. So here's the system. On the left we have hemoglobin in the blood and oxygen. On the right we have oxygen bound up to the hemoglobin, and in your body those are in equilibrium. In the lungs there's a high concentration of oxygen gas surrounding the blood. This causes the system to shift to the right, and it causes oxygen to bind up with the hemoglobin. In terms of Le Chatelier's, we would say we're adding a gas phase product, so the system reacts to shift away from reactants and to favor products. In your tissues, though, the blood enters a region where the surrounding tissue is depleted in oxygen, so oxygen unbinds from the hemoglobin, and the system shifts to the left to favor increased concentration of the oxygen in the gas phase. The oxygen, of course, moves to your tissue where it's used to burn sugars. If we come back to the Freon system for a minute, we can also demonstrate the removal of a product will shift in equilibrium to the right as the system continues to counteract the disturbance. And again, it's important to remember that the concentration of the product removed must be affected. And in this particular case, the Freon and the hydrogen chloride are both in gas phase. So if we remove either one of those products, we're going to affect its concentration. So here's the graph. And again, the hydrogen fluoride starts at some positive value and it drops. The hydrogen chloride, which is a product, and the Freon, which is also a product, both increase. They both start at 0 because we have no products initially, but then they both increase as the reaction proceeds. The hydrogen chloride, of course, increases twice as fast as the Freon because the stoichiometry is 1 Freon molecule is produced for every 2 hydrogen chloride molecules. The stress we introduce to this system is the removal of one of the products. We're removing some hydrogen chloride here at equilibrium. So we're removing a product, and the system will shift to the right to increase production of those products. And we see that in response to this stress, concentration of hydrogen chloride and concentration of Freon both increase, while the concentration of hydrogen fluoride decreases. I think I might have said hydrogen fluoride. I meant hydrogen chloride. So hydrogen chloride increases, Freon increases, and hydrogen fluoride decreases. Collision theory explains this shift in equilibrium by changing concentrations in terms of the probability that effective forward and reverse collisions will occur. If you increase the concentration of a reactant, say the hydrogen fluoride, you increase the likelihood of an effective forward collision. Therefore, you increase that forward collision rate. And we've sort of spelled that out here. The forward reaction therefore increases in rate until the effects are overcome, and they're overcome by a production of sufficient products to again equalize the reverse effective collision rate with that of the forward rate. And it's important to be mindful that changing the amount of solid or liquid phase material, you change the available surface area for both forward and reverse reactions. More importantly, you don't impact on their concentrations. So as a result, the equilibrium does not respond to changes in the amount of solid or liquid phase species present. It's for the same reason we do not include their concentrations in our Kc calculations. Temperature is a little more complicated. To understand the effects of temperature, we have to consider endothermic reactions and exothermic reactions separately. And we've seen this previously. For an endothermic reaction, energy can be thought of as a reactant going into the system. And for an exothermic reaction, energy can be thought of as a product coming out of the chemical system. And by way of example, aqueous hydrogen chloride is manufactured using an endothermic process. And we can heat that process. By heating it, we're, for all intents and purposes, adding a reactant, and the system will shift to the right to favor increased production of products. On the other hand, a step in the industrial manufacture of sulfuric acid is exothermic in nature, and it's run at low temperature to again force the system to shift to the right to favor product production. So here's an exothermic system. By cooling it, we're removing a product. We're causing the system to shift equilibrium to the right to favor manufacture of the products. How do we reconcile these findings with collision theory? We would say that the removal of the energy causes both forward and reverse reaction rates to slow in the case of this manufacturing step in the process of producing sulfuric acid. It's just that the reverse reaction rate will slow more than the forward reaction rate. There's a very important additional factor to consider when we consider temperature impacts on equilibrium. The actual value of the Kc is temperature dependent. And if you scroll back to our discussion on the Freon reaction, we reported Kc at 500 degrees Celsius. Because temperature is the one influence on an equilibrium system that we study that actually impacts the value of the Kc expression. It's unique in that respect. Temperature is further complicated by questions of thermochemistry. Le Chatelier's principle is not the only factor to consider when we consider temperature's impact on a chemical system. Any chemical system must be run hot enough to overcome activation energy, or no reaction will take place at all. And it's for this reason a great number of industrial processes take place at high temperatures, even though they're exothermic. The Haber process is one such process. It's operated at 500 degrees, even though it's exothermic. We have to do so to supply the activation energy for both the forward and reverse reaction to occur at all. And otherwise, both processes are far too slow for it to be industrially valuable. Let's talk about pressure. Boyle's law is a gas law that says pressure and volume are inversely proportional. So if you half the volume of a gas phase system, you double the pressure in the system. And pressure is a function of a couple of things. It's a function of gas particles striking the walls of its container and the kinetic energy with which those gas particles strike the container. The system will shift in response to a pressure change by reducing the stress, by reducing the overall gas pressure if you've increased it. It will shift to the side of the system with a fewer number of particles because that will decrease the collision rate between particles and the walls of the container. And here's one such example. We've got 3 gas phase particles on the left of this system in equilibrium with 2 gas phase particles on the right. So if we increase the pressure in the system by decreasing the volume, so we've cut the volume of the container in half, therefore we've doubled the pressure, the system will shift to the right to reduce the total number of particles in the system and thereby to reduce pressure. An interesting side note here though is if you add a gas that doesn't participate in the chemistry, add an inert gas like argon and equilibrium will not shift. So it's not really a function of pressure that we're talking about here. What we're talking about is by adding gas that doesn't participate in the reaction system, we don't change the concentrations of the particles that do participate. Volume change impacts upon pressure, but it also impacts upon concentration. By halving the volume of the container, we're doubling the concentration of the particles. Collision theory would say that as you increase the pressure by reducing volume, you also increase the concentration of all gas species in the system. You therefore increase the rate of the forward reaction more than the rate of the reverse reaction because you have more reactant particles in the system. Therefore, you increase the effective collision rate of the forward reaction more than you do increase the effective collision rate of the reverse reaction. So again, masked in this concept of pressure is really a consideration of concentration. The system is reacting to return the relative concentrations of all species to reflect the Kc expression. As we've seen, a catalyst works by providing an alternative pathway for a chemical reaction to take place, one that has a reduced activation energy. And we've seen that catalysts reduce the activation energy not only for the forward reaction, but also for the reverse reaction. So as a result, catalysts do not affect the equilibrium position of a chemical system. They increase both forward and reverse reaction rates to the same degree. And I've just spelled that out here for you. And as a result, therefore, catalysts do not trigger a system to shift its equilibrium position. And that's the end of my lecture. I've got a few questions I've cobbled together. Let's have a look at them. Which of the following would increase the equilibrium concentration of nitrogen monoxide? Nitrogen monoxide here is a product. You notice there's 9 gas phase particles on the left and 10 gas phase particles on the right, and it's an exothermic system. If I decrease the volume, I increase the pressure, the system's going to shift to the side with fewer particles to reduce pressure. In this case, it's going to shift to the left because there's only 9 gas phase particles there. There are 10 gas phase particles on the right. More importantly, that will not increase the nitrogen monoxide present, so 1 is out. Secondly, increase the temperature. This is an exothermic system. Energy can be thought of as a product. By increasing temperature, then we're adding a product, and that'll shift the system to the left. So increasing the temperature does not increase nitrogen monoxide production, and the answer, therefore that's not our answer. 3. Adding ammonia. Ammonia is a gas phase reactant. By adding a reactant, we shift the system to the right to increase products, in this case increasing the nitrogen monoxide concentration, and 3 is the only correct answer. Therefore the answer to the question is C. Which condition should favor the maximum yield of carbon monoxide? Well, we're looking at a system that is endothermic, so energy is a reactant. If we heat this system, we're going to add a reactant, and we're going to drive it to the product side, increasing the yield of carbon monoxide, which is what the question wants us to solve for. So this is a high temperature system. A and B are out. Then the question is one of pressure. You'll see I've got 1 gas phase particle on the left and 2 gas phase particles on the right. If I reduce pressure, the system is going to shift to the right to increase the number of particles to reestablish the original pressure. So the answer is high temperature and low pressure. The answer is D. Consider the following equilibrium reaction. The addition of a catalyst. And we can almost stop reading right there. A catalyst do not shift equilibrium. So the addition of a catalyst to this reaction would increase both the rate of the forward and reverse reactions. D. Consider the following equilibrium. What happens when calcium oxide is added? Well, the answer there relates to its state. It's a solid state. Does not impact on equilibrium position. The answer here is A. There's no shift. Which of the following describes the temperature and pressure needed for maximum yield? Endothermic system. If I add energy, I'm going to drive the system to the right, increasing yield. Therefore, A and B are out. We're talking about a high energy system, high temperature system. The question of pressure. I've got 1 particle on the left and 2 particles on the right. To drive this thing to the right, I want a low pressure system, and the answer here is C. Consider the following equilibrium. The equilibrium shift to the right if, well, this is an endothermic system. If I heat this, it'll drive the system to the right, and the answer is C. Here's an interesting graph. Given the above disturbances at the 3 vertical lines in order, the system will shift to the, well, this green line reflects the concentration of the iron 3 ion, and that's the original stress at the first vertical line. So you're adding a reactant, an aqueous phase reactant in the system. The system will shift to the right to reduce its concentration and to increase the concentration of the red product. So the first shift in response to the first stress is red, and A and B are out. At the second vertical line, we're adding this thiocyanate ion, which is the other aqueous phase reactant. By adding it, the system reacts by reducing the concentration of the reactants and increasing the concentration of the product, the red colored product. So again, at the second vertical line, we're looking at another red shift, and the answer to this question is C. Here's one final graph. I think I'll leave these two questions for you. I'll also refer you to any homework your teacher assigns, and we'll see you next time when we talk about the auto-ionization of water. Thank you.